Hey guys, welcome back to AP Precalc. This is lesson 1.8. Let's get right into it. All right, so here's a bell ringer for today. Pause the video if you haven't done this already, because I am about to go over the answer. All right, so here we have a rational function, r of x, which is given by that fraction of two polynomials on top of each other, and we want to know what statement about the end behavior of this function is true. And so to find the end behavior of a function, we only want to look at the leading term. So that -9 and that +3 are kind of irrelevant, and we're really only looking at 2x over x squared. This is going to classify or fall into a bottom-heavy function because the degree in the denominator is bigger than the degree in the numerator. Because this is the case, this function is going to tend towards 0 as you go to the left forever and as you go to the right forever. What it looks like is if you have a graph like this, may look like that. This is just an example, and you'll have a horizontal asymptote at y equals 0 right there, where this function is going to get super close to 0, but never touch it. So how would we write that in a verbal form? Well, let's write our two limit statements, right? You can write the two limit statements here. The limit as x approaches -infinity and as x approaches positive infinity of our function r of x. And because this is bottom heavy, it's automatically both of these are going to be 0. So now let's see if we can match one of these with a limit or with a verbal limit statement. As the input values of r increases without bound, so that's going to be as x goes to positive infinity. Unfortunately, that's all of these, so it doesn't help us. The output values should not decrease or increase, but they should get arbitrarily close to not 2, but 0. So C is our answer, and it matches our right-hand limit statement there. Of course, you don't need to write out the limit statements on like a test. This is just to show you what that verbal translation means in terms of a limit statement. All right, so now the domain. To find the domain of a rational function, which remember a rational function is just two polynomials on top of each other, all you need to do is just remember don't divide by 0. We can basically plug in any number into this rational function that we want. You know, maybe 1, 1,000, 10 billion, and 5, whatever number you want, as long as you're not going to get a number over 0 in the denominator. So basically figure out where that denominator is equal to 0 and basically take those numbers and tell them, hey, get out of here. You're not part of the domain. We're restricting you from the domain. Otherwise, you can plug in any other number or all real numbers because when you divide by 0, like I showed you on day 1, crazy things happen where you can prove that 1 equals 2 when you divide by 0. So for example, if we have 2x plus 3x squared minus 4 all over, let's say, x minus 3, you just want to see where is the denominator equal to 0, and that would really only be at x equals 3. And so our domain here, we would write all real numbers except x equals 3, and that would be enough for the domain there. All right, now the zeros. The zeros is when the equation is equal to 0, right? Obviously. But remember, when we're dealing with fractions, 0 over any number will always be 0, right? 0 over 7 is 0. 0 over 1,001 is 0. So it doesn't matter what's at the bottom. We just want to figure out, now this time, where's that numerator equal to 0? And those are going to be our zeros except for one exception. And that exception is if you come across something like, let's say, x minus 3, x plus 4 over x minus 3, where at x equals 3 is a 0 in the numerator, but when you plug in 3, you also get a 0 in the denominator, which is bad. We would have to exclude this, right? In terms of our zeros club, x equals 3 is not going to be a part of that because it also is restricted from our domain from what we just learned. And so here, our only 0 of this function should be let me simplify this function. Our only zero of this function should just be x equals negative 4. Another example is if we have 2x minus 3 over x plus 1. Let's see, where is our numerator equal to 0? So set it equal to 0 and solve. X equals 3 over 2. So that should be our 0. And you can just write it as x equals 1.5 or, I shouldn't have put a fraction, or you could write or 3 over 2, but like that could be your answer is how you write your zeros, x equals, and then whatever numbers are your answer there. All right, so let's try example 1. Find the domain and the zeros of the following function. And I'll say before we even begin, or before I work through example 1, it's important to note that to answer these questions, it's extremely beneficial to have our rational function in factored form. Right? You can work with it when it's in standard form, but you're going to have to convert to factored form before you do anything else. So A is a little easy for us, right? If we take a look here, let's work on our domain first. Our domain is going to be all real numbers except x equals 2. Where else is the denominator equal to 0? X equals negative 3 and x equals negative 5. So that's our domain. Now, where's our numerator equal to 0? This is at 1, 4, and 2, but unfortunately 2 is part of our restricted, part of the numbers that are restricted from our domain. So our zeros here are just going to be 1 and 4, right? 2 is not part of the zero club. It's part of the restricted domain club. Right, now looking at B, we actually want to factor this equation and get it in factored form before we even touch it, trying to find zeros and domains. So if we factor the top, you should get x, factor on x from all three terms, so plus 11x plus 30, all over, and then we can factor the bottom as well. X, let's see, minus 2, x minus 3, and then we can even factor that trinomial in the numerator as x plus 6, x plus 5 over x minus 2, x minus 3. All right, now that we have this, our domain is going to be all real numbers except x equals 2 and 3. Positive 2, positive 3. And then our zeros here are x equals 0, negative 6, whoops, and negative 5. It's important to note that because we don't have any repeats in the numerator as the denominator, all of these numbers are zeros, right? If we did see them pop up, that like same linear factor pop up in the denominator, we would exclude them from being a part of the zeros. All right. Now today's main focus is going to be learning how to solve rational inequalities. And so what these are is essentially a rational function, let's say maybe like 2x minus 1 over x plus 5. And we're going to be asked, where is this either greater than, less than, greater than, or less than or equal to 0. And it will always be the number 0, at least for now. And so that will be what we have to deal with. We want to solve these and figure out exactly what numbers can we plug in that gives us a negative number as an output. All right. And so there's a few steps. I'll go through all 5 with you step by step with an example problem and then let you try some on your own. All right, so step number 1, make the function easy. What I mean by this is sometimes I'll be generous and I'll give it to you in factored form and you don't even have a step 1 at that point. But other times I may challenge you, is the way I like to put it nicely, to make sure that you know how to factor and ask you to put it in factored form, because to solve this you will need it in factored form. And so step 1, make the function easy by factoring if you can. So this is the example that we're going to work through. We're going to solve x minus 2 over x squared plus 9x plus 18 is greater than or equal to 0. So factoring the numerator this is already done for us. And then if we factor the denominator, you should get x plus 6, and then x plus 3 would be how I would factor this. And so this should be our factored form. And so that is step 1. Step 2, so what I'm going to have is I have in black what we did from the previous step, kind of copy and paste it onto each slide. Step number 2 is find the critical values. This doesn't really have anything to do with domain and range. All we just want to find is any number that makes the numerator equal to 0 or the denominator equal to 0. Here we see 2, I see -6, and -3. Those are going to be our critical numbers. So our critical numbers here will be x equals 2, -6, and -3. All right, once we have our critical numbers, we want to make a sign chart. And so you want to use those numbers and kind of graph those 3 on a number line. Space them apart, right? Give them enough space. So -6, -3, and 2. All right, now at each one, we want to determine if we are going to mark that point on the number line at -6, -3, and 2 with either an open circle or what we have here, a closed circle. And so how do you determine whether is -6 open or closed, is -3 or is -2 open or closed? How do we know that? So pretty much any number that comes in the denominator, right, when we plug that number into the equation, that would never make the inequality true. And the reason for that is because then you're just dividing by 0 at that point, which we don't want to happen. So we are going to mark any 0 that comes from the denominator with an open circle automatically. All right, so here, -6 and -3 are going to be both open circles. Then if we have a less than or a greater than inequality sign, just with those two, everything in the numerator and denominator will be open circles. So open circles for all the critical values. If you have a less than or equals to or a greater than or equals to sign, it's going to be open circles for your denominator critical values. And then it will be closed circles for your numerator critical values. Right? So here this is a less than or equals to. So because it has that equals to part, and 2 comes from the numerator, we are going to mark this with a closed circle. So this is how our sign chart should look right now. All right, the final thing, step number 4 is plug and chug. So we want to see, is any number after -6 going to make this inequality true? Is any number between -6 and -3 or between -3 and 2 or greater than 2? Are any of these numbers going to make this inequality true? And so the only way to do it is just by plugging in testing points and checking. So let's see. A number that's less than -6, I like to go with nice integers, so -7 here. Between -6 and -3, I'll go -4. Between -3 and 2, I like to do 0. So if I can, I like to plug in easy values like 0, 1, -1. Right? And then greater than 2, I'll just go with 3 here. So these are going to be our testing points. So let me show you with, let's do 0 first, right? What we actually want to do is plug 0 into this equation. So this is going to become 0 minus 2 over 0 plus 6 over 0 plus 3. And then we want to see, is this inequality true where this is, just greater than, or equal to 0, right? Is this true? So plugging 0 in the numerator you get -2. In the denominator we get +6. And then in the other denominator, that factor, we're going to get +3. and we want to see, is this greater than or equal to 0? Now, because it will always be greater or less than or greater than or equal to or less than or equal to 0, we're basically asking, is this going to be a positive number, right? Any positive number is going to be greater than or equal to 0. And so, if we take a look here, we have negative 2 over 18, but we basically have a negative over two positives, which is going to be a negative over a positive, which is a negative number. So this is not greater than 0, so we're going to mark this entire interval with a big fat X. There. All right. Once we have that, what we want to do is we want to do this for each of the other three testing points. And now we know any time or any number in between -3 and 2 will not be part of this inequality, will not make this inequality true. Finding the rest, you have 3 minus 2, which is 1. So I'm just going to put each number in here. 3 plus 6 is 9, and 3 plus 3 is 6. Is this number going to be positive? Which 1 over 9 times 6 is 54, but it's just all positive numbers, right? So this should be, so I'm going to mark this with a big fat check mark there. Taking a look at plugging in -4, you would get -6 in the numerator over 2, and then -1 in the denominator. This should be a negative over, this should be another negative number. So a negative over a negative is a positive number, so this is going to hold true. So that's going to be a check mark as well. And then finally, -7, we should get -9 over -1 times -4. Is that greater than or equal to 0? This is a negative over a positive number, so this should be no. This is not greater than 0. All right, so once you have your check marks and your X's, then it's pretty easy to go from there. Pretty much anytime you see a check mark, you want to include that as part of your solution set. That's part of the values that make this inequality true. So because we had two inequalities there, then remember, you're working off of your critical points, right? -6, -3, and 2. These are just testing points, so don't get confused. But what this means is any number in between -6 and -3 is going to hold true and make this inequality true. And any number greater than 2 or including 2, because this is a closed circle, will make this inequality true as well. So how do we convert the sign chart to an inequality? Well, you can do inequality or interval notation. I'll show you both. So inequality, and then we'll do interval. Inequality-wise, anytime x is between -6 and -3, or you could put and, anytime x is greater than or equal to 2, that would be this in inequality form, right? Notice how we don't have like less than or equal to infinity. You don't write that when you're writing inequalities, so we can kind of get rid of that right there. Let's see. So let's get rid of that. And now interval notation, this is going to be open bracket, -6, -3, open bracket, a union to connect two intervals. And then because we are including 2, it's going to be a square bracket 2, and then curly bracket around the positive infinity. That would be our interval notation. I'm okay either way as long as it's correct. So I will accept either one on like a short answer, potentially on your next quiz. All right, so example number 3. Solve this. I was nice, gave it to you in factored form, saved you a step. So try this, and then we will pause the video now, try this, and I'll go over the answer right now. All right, so here our critical numbers are x equals 1, -6, and -2. So I want to graph those on my number line. So -6, -2, +1. Now I'm going to do this in a different color just so I don't get confused. I'm going to start plugging in values. So 0, 2, -3, and then -7. And then I want to see, is this whole thing going to be a negative number? But before I do that, let's actually fill in or give these open or closed circles. So x plus 2, which means -2, is in the denominator, so that's an automatic open circle. However, at 1 and -6, these are both in the numerator, and this has an underline there. So we're going to turn those into closed circles. So -6 and -1 there. All right, now let's plug them in. So we're plugging them into that function, really just seeing if you get a negative number. If you do, it's a check mark. If you don't, it's an X. So plugging -7 in here, you should get -8 times -7 plus 6 is -1 over -7 plus 2 is -5. This is going to be a positive over a negative, which is a negative, which is less than 0. So that's going to be a check mark. Here, you should get -4 times 3 over -1. This is a negative over a negative, which is a positive number, which does not make this negative, so that should be an X, plugging in 0, -1 times 6 over 2, and that's why I like nice values like 0. This is going to be a negative over a positive, which is less than or equal to 0, so that's going to be a check. And then 2 here, we have 1 times 8 over 10. Sorry, this should be 4, geez. But still, it's a positive number, so it's not less than or equal to 0, so that's going to be a no. And so marking our inequality, it's going to be anytime x is less than -6, and anytime x is between -2 and +1, not including -2. So our inequality and our interval, I'll write both. Inequality-wise, anytime x is just less than -6 or equal to, anytime x is between -2 and 1. In interval notation, this should be -infinity to -6. This should be square bracket, union, curly bracket, -2, 1, square bracket, and that should be our answer for example number 3. Example number 4 and 5, pause the video now because I'm about to go over these. Here we want it in factored form, so this is going to be x plus 2, x minus 2, all over, this should be x minus 5 squared, I'm pretty sure. Yep, is less than or equal to 0. So our critical numbers are -2, 2, and +5. So plotting those here. And then finding our points that we can test. So 0, 3, 6, and -3. Once we have this, we know -5 is in the denominator, but all 3 of these should be open circles because this is not that, because there's no underline. So no underline, no closed circles. So all 3 are open here. Now just testing points. I like to test it into the factored form just because it's a lot easier for me. And so here we have -3 plus 2. This is -1 times -5 all over -3 minus 5. This is -8 squared. And we want to see, is this a negative number? Is it less than 0? You have a positive over what would be a positive, so this is going to be no. Plugging in 0, you get 2 times -2 over -5 squared. This is going to be a negative over a positive, which is negative, so this should be true. Yes, check mark. Plugging in 3, you get 5 times 1 over -2 squared. This is not going to be a negative number. It's going to be all positive, so this is going to be a no, an X. And then finally we have a 6. So here 6 plus 2 is 8. 6 minus 2 is 4 over 1 squared. So this is also going to be positive, so this should be a big X, a no-go. And so our only solution set should be right there, which means we're going to have from -2 to 2 is going to be one of our answers, or you could have that as your second answer there. All right, example number 5 here. We also need to put this in factored form. So factoring the top, you should get x minus 5, x plus 2, all over x plus 8. Where is this less than or just less than 0? So our critical numbers should be 5, -2, and -8. Plugging those in on the number line, we can plug in 6, you can plug in 0, -3, -9. Because this is just less than and not less than or equal to, all three of these bad boys are going to get open circles, giving them out like Oprah. All right, so plugging these numbers into the inequality, we want to see, is this just less than 0? So is this going to be a negative number is what we're asking. So here, we'll start with -9. -9 minus 5, -14, plus 2 is -7, all over -1. So this is going to be a positive over a negative, which is less than 0. So that is going to hold true. Plugging in -3, we get -8, -1, all over +5. This is a positive over a positive, which is not less than 0. So you can eliminate that one. If we plug in 0 here, you should get -5 times 2 over 8. This is a negative over a positive, which is a negative. So yes. And then plugging in 6, we get 1, 8 over 14. This is definitely a positive number, so this is going to be no good. So here, our inequality should look like that. Right? And now just converting this from inequality notation to, or from the sign chart into inequality or interval notation. So in inequality notation, this is going to be anytime x is less than -8. Whoops, I accidentally put -infinity. This should be -8. And -2, x, and 5. So that'd be inequality form. An interval form, this should be -infinity to -8, union -2 to 5, other union. So that should be our answer here. I would have accepted either one of those. All right, so we're done going over those in terms of your notes. Now, example number 6 is just looking at this graphically. So the graph of a rational function f is shown in the figure above. Use the graph to solve the following inequalities. So what we have here is, this is kind of what we're doing to solve the inequalities, except instead of using equations and doing all the steps we just did, we're just going to look at it graphically, right? Pretty straightforward. So here we want to see where's our y values less than 0, and that's going to be at those two lines there. So I would write these in interval notation, but it's going to be from -3 all the way to x equals -1, but not including, actually we would include 0, so this should be square bracket there. But we don't include -3 because it won't touch -3, but we do include -1 because it would be equal to 0 there. Union, square bracket 2, and then we're going from 2 to +3. So that should be our answer for part A. All right, looking at part B, we'll use green. Where is this just greater than 0? So that's going to be this line segment right there. this line segment right there, and then that short part right there, not including -1 and +2, because it's just greater than, not greater than or equal to. So the first one should be from -infinity all the way up to -3, not including it, union -1 to 2, not including either one of those endpoints, union 3 to +infinity. That would be our answer for part B. And then part C, what we have here is where is this greater than or equal to 1? And so we want to, again, look at this part here. And so taking a look, this is 1 right here. So where is it greater than? It's going to be that line segment and that line segment. So this should just be -infinity to -3, union 3 to +infinity. And this should be our answer here. One other thing to note that I may not have talked about before, but this should be a curly bracket, not a square bracket. So sorry if that was misleading. All right, so that should be it for 1.8. If you have any questions, please come into office hours, and I will see you guys later.